Pandale. I'm a PhD student in the Mechanical Engineering Department of the University of Texas at Arlington. Today I'm presenting a topic, power cycling thermal fatigue impact on the solder joint reliability of the package. In the realm of electronic packaging, a fundamental understanding of a failure mechanism is critical to ensuring a product reliability. Modern electronic devices are constantly evolving towards miniaturizing and the increasing functionality, demanding a compact and efficient packaging solution. Wafer-level chip-scale packages, WLCSP, have emerged as a key technology to meet this demand, offering a direct extension of a wafer fabrication. However, the operational condition, particularly power cycling, can induce significant stress on these packages, leading to reliability concerns. In essence, the final device is a die featuring an array pattern of the solder interconnects. The difference of a WLCSP from the BGA and a laminate CSP is due to the elimination of the bond wires and interposer of the connection. WLCSP offer advantages such as a smaller form factor, cost effectiveness, and enhanced thermal performance. However, they can also exhibit relatively shorter solder life compared to other packages. Power cycling, defined as the repetitive act of turning electronic device on and off, is a common occurrence due to transient processing behavior. In contrast to temperature cycling test, power cycling simulation offer a more realistic representation of the operating condition because the power cycling results in a non-uniform temperature distribution, as the die act as the primary heat source. This non-uniform temperature distribution and the difference in the coefficient of thermal expansion of each component within the WLCSP leads to a complex potential damaging problems. This research investigates solder joint reliability in a WLCSP by simulating power cycling and calculating resulting stress and strain. A critical aspect of this analysis is understanding how varying the PCB thickness influences the overall reliability of a solder joint connection under power cycling load. To accurately model this behavior, a finite element analysis approach is used. The model is constructed according to the package dimension and appropriate material property are assigned. A transient thermal analysis is then performed, applying a power cycle to the die. The resulting temperature distribution from the transient thermal simulation of the package is then transferred to a static structural simulation for thermomechanical analysis. In this study, simulations were performed using 3 power cycles to perfectly capture the viscoplastic behavior of the solder joints, where plastic were captured for the 3rd cycle after the stress strain gets stabilized. Plastic work, a key damage metric, is nothing but a strain energy density, which is used and captured in this analysis. The corner solder joint consistently exhibit the maximum plastic work due to higher CT mismatch. The equivalent stress on the solder joint is higher in the 1 mm compared to 0.7 mm board. The number of cycles to failures is known to be inversely proportional to the plastic work based on the Schubert's and Sayed's model. Similarly, the 1 mm board is predicted to fail earlier due to its increased thickness and reduced flexibility, stressing the solder joint at the corner. PCB material properties were characterized using a thermal mechanical analyzer and a dynamic mechanical analyzer, and then these data were subsequently used in the FEA. In the poster, we have not gone into detail of how the testing been performed in the TM and DMA, but the PCB properties were extracted using this test. In the conclusion, power cycling simulations were performed and the critical solder joint were identified. Change in plastic work were obtained and the number of cycles to failures were estimated to provide the quantifying difference in the reliability between the boards and under the power cycling condition. At the end, I would like to thank my professor, Dr. for providing the consistent support and guidance throughout the work. Thank you so much.